Hi, welcome to another video on grade 12 chemistry. In this few videos, we're going to focus on chemical equilibrium, and we want to see and understand how chemical equilibrium takes place and how we can manipulate these types of reactions. Without further ado, let's see what this video is all about. First, we're going to look at some introduction and the different parts that we will cover in this series of 3 videos. In the first part, we look at the basic theory, closed system, what is a dynamic equilibrium. We're also going to look at what is Le Chatelier's principle, and a little bit deeper, we'll look at factors that will influence equilibrium. And very importantly, we must understand some basic terms and definitions. In the second part, we're going to look at effects of concentration, temperature, pressure, and a catalyst on equilibrium graphs. And we're going to see if we can answer some questions regarding these particular factors in exam questions. And then the third part of this series is equilibrium constant, or Kc. And we're going to see and try to understand what the expression is all about. How can we have low values of Kc and influence those values, and how can we have high values and influence those Kc values? We also want to understand what are low and high Kc values, and then once again we'll look at exam questions. Okay, some basic theory. So first of all, we need to understand what is an open system and what is a closed system. An open system is basically one that continuously interacts with its environment. That means that mass can go from the system and then enter the system. Or we will have energy that will leave the system and energy that will enter the system. So both those particular quantities will enter and leave the system. In a closed system, we're going to have where only the energy is going to leave or exit the system. No mass is going to leave the system or enter the system. That's a closed system. According to our definition, remember that a closed system is an isolated system from its surroundings. And once we know these two parts, we can apply to a special type of reactions, and in this case, it will be reversible reactions. Now you have to understand that the reversible reaction is different from the previous reactions that we've studied that runs to completion. In a reversible reaction, we have reactants, and look at our example reaction here is that reactant A reacts with reactant B, and those two will form products C and D. In this particular case, if it's a reversible reaction, the products C and D must recombine or react with each other to form the original reactants. If that happens, we have what we call a reversible reaction. And this reversible reaction is always indicated with a double arrow. Now you can use slightly a half arrow at the top and a half arrow at the bottom, or you can use 2 full arrows. It doesn't really matter, but as long as your arrows are going in both directions, that will indicate that it's a reversible reaction. Now remember that in reversible reactions, both the forward reaction and the reverse reaction are taking place at the same time, or they occur simultaneously. Now, in the following slide, if we want to look at the dynamic equilibrium, here I have an example of crystals in my beaker, and these crystals are heated. These particular crystals that I've got here is called copper sulfate pentahydrate, or we can basically refer to it as hydrated copper sulfate. And it generally has a blue color. Now, these are crystals, it's copper sulfate, but it has water molecules locked between the copper sulfate molecules inside of the crystal. And because of the water, it gives it a nice blue color. And if you heat these crystals, the water is released, it evaporates, and what's left over, you'll find a kind of a grayish white crystal, and this is called copper sulfate, or more commonly known as anhydrous copper sulfate. do take note that anhydrous means without water. So here I have the white anhydrous copper sulfate. Now, if you're going to prepare this in the lab, it generally will have a grayish-white color. And the intensity of that color depends on how much water has been released. If you still have a little bit of water, it will have a little bit of a blue tint into the crystals. And that's how you can produce these products, by taking the hydrated copper sulfate, heating it, and then getting your grayish white copper sulfate crystals. And if you want to go back, all you need to do is you just add water, and then the reaction will go in a reverse reaction direction, and you will form the original blue crystals. And that's a typical dynamic equilibrium that has been set up. Easy to do, but anyway, let's take that information and see how we can actually write down a few things that we've learned about this particular chemical reaction. Now, the forward reaction will take place from the hydrated copper sulfate, and it will be converted to the anhydrous copper sulfate. We've mentioned that, and just a recap. You can cause the reverse reaction to take place again by adding water to the anhydrous copper sulfate, and that will cause the crystals to take in the water and form the original hydrated copper sulfate. So this is a typical chemical reaction where both the forward reaction and the reverse reaction will take place. When that happens, and you find that both reactions are taking place, but they're taking place at the same rate. So the rate of the forward reaction equals the rate of the reverse reaction. You have what we call a dynamic chemical equilibrium, or just short, a dynamic equilibrium reaction. Now, in this particular case, the way I explained it is that I first refer to the forward reaction, then I mention the reverse reaction. When you have these crystals in the lab, the reaction takes place continuously. However, from your point of view, when you observe the reaction, you will see mostly one color that will dominate over a long period of time. What we don't see is that the reaction takes place on a microscopic level. So if you see more blue, it means that the reaction has more blue crystals compared to white crystals. If you see more grayish white, it means the reacting mixture, or the container that you have it in, will contain more anhydrous copper sulfate and less hydrated copper sulfate. So what you see is not always what happens at the microscopic level. Okay. Now, one of the things that you must take note, when a dynamic chemical equilibrium exists, it means that the amount of reactants and the amount of products remain the same, or they stay constant. So over time period, no change will occur in either in the reactants of the concentration of the reactants, or the concentration of the products, okay? Or the number of moles of the reactants per volume, or the number of moles of products per volume. So when I refer to the amount of substance, I'm referring to the number of moles. But one can also say, because the volume remains constant, that in this case, the concentration of the reactants and the concentration of the products remains constant. So that's not going to increase, it's not going to decrease, but the dynamic equilibrium still exists. Okay, now for dynamic equilibrium to come into effect, we need some requirements, and there are two basic requirements. And remember that both these requirements must be met. The reaction has to be a reversible reaction. I'm going to indicate it with a double arrow here, and the system has to be closed. It cannot be an open system, it must be a closed system. Okay, Le Chatelier's principle, and this is a principle that we need to know. Now, Le Chatelier observed chemical equations, and he came up with the following principle to help us predict what's going to happen if there are any changes in equilibrium. And he basically stated, when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. And this particular principle also tells us and helps us understand how we can understand and predict what's going to happen. Now, any chemical equilibrium can be influenced by three factors: concentration, temperature, and pressure. Here we have an equation, a fictitious equation. Reactant A reacts with reactant B, produces product C and product D. Now I've got colors that will indicate to us which particular reactant or product we refer to. If the concentration of the reactant increases, that could be A or B, that will cause that the concentration of the products will increase. And what will happen is, by increasing the concentration of the reactants, the system will react in such a way by decreasing that particular factor, and in other words, use up that increase in the concentration, and then in that way produce more products. And in doing so, reestablishes a new equilibrium. So do take note of that. If we're going to increase the product concentration, then the opposite is going to take place. The system is going to try to decrease the product concentration, use it up, and in doing so, it's going to favor the reverse reaction and then produce more of the original reactants. So those are the two main things that will happen with concentration. Now here what I've used, I said the increase of concentration of the reactant. But remember, if I want to know what's going to happen if I decrease the concentration of the reactant, then it's the opposite of this. If I want to decrease the concentration of a product, it's going to be the opposite of these 2 points that I've raised here. Now, temperature, before we could understand what temperature is and how temperature influences the reaction, you need to identify which of those reactions, either the forward or the reverse reaction, is favored by the is favored by temperature and is the endothermic reaction. Now remember, an increase in temperature will always favor the endothermic reaction, and a decrease in temperature will always favor the exothermic reaction. So in order for you to understand and know which one is an endothermic reaction or which one is an exothermic reaction, you have to first go and identify this in the equation. Now, pressure is the last factor, and pressure can only influence the chemical reaction if there are gases. And you have to have more than one gas, either in the products or in the reactants. If there are one of the products or reactants that are not a gas, for instance, it's a solid or liquid, then just remember it will not be influenced, because we know pressure doesn't influence those two phases of matter. Increase in pressure will then favor the side with a fewer total number of molecules or number of moles. And a decrease in pressure will favor the side with more molecules or number of moles. So the way that you're going to do this is to add up the total gas molecules on the product side and to add up the total gas molecules on the reactant side. If those molecules or the number of moles, you can add up the number of moles. If it's the same on both sides, then you know pressure is not going to influence the equation. However, if one side is more than the other side, then the side that is more will be influenced by a decrease in pressure. In other words, if you decrease the pressure, the equilibrium will change in such a way that the reaction leading to the side that contains more molecules or more moles will be favored. And the opposite will happen if the pressure is increased. Okay, I know that was a mouthful, but we'll come back to that in our later slides. Okay, let's look at some basic terminology. And in this case, I'm going to list the terminology as it appears in the subject guidelines. Now, open system, we need to know what an open system is, what's a closed system, and we need to understand and be able to define what is a reversible reaction, what constitute a chemical equilibrium and be able to define that. And we need to be able to identify the different factors that influence a chemical position. And we must be able to give or define Le Chatelier's principle. Now remember, these terms are very important and pay attention to it. Now, remember that each definition that you're going to get in exam question paper counts 2 marks. And if you're going to leave out those particular questions and you're unable to answer it, you will lose easy marks. And that way you will actually have a more difficult time trying to answer some of these questions, because these definitions are also applied in your longer questions. So it's an easy way to gain marks. So try to understand and try to memorize these particular definitions. Okay, let's look at how we can apply Le Chatelier's principle. But before we're going to do that, we need to have a understanding the steps in explaining how Le Chatelier's principle can be used. Now, point number 1, identify the disturbing factor. Now remember the acronym TCP, temperature, concentration, or pressure. If you identify the factor, you must be able to say it is an increase or it's a decrease. Sometimes you don't have to identify it, and sometimes I will give it to you. But take note that is an increase or decrease. Don't say a change in temperature, because we know that a change refers to both increase and decrease. So be specific. Second step that you're going to look at is state that the system will act in such a way that it will oppose the disturbance. So you must say that the system will try to oppose the factor. So if your factor, for instance, is an increase in temperature, then state that the system will attempt to decrease the temperature. Point number 3, so that because of what the system is going to do, state how it's going to influence your reaction. Is it going to favor the endothermic reaction? In this case, if it's temperature, is it going to favor the exothermic reaction? Or you can say, is it going to favor the forward reaction, or is it going to favor the reverse reaction? Okay. So when it comes to temperature, you have to mention which reaction is it favor, endo or exothermic, and you have to state, is it going to favor the reverse or the forward reaction? And then lastly, you need to state, depending on the question, which concentration is going to favor it. Is the concentration or the number of moles of the products going to be favored or increase? And the same if it's going to affect the reactants. That will be more clear in the question, because the question will ask you, how will it affect the concentration of either the reactants or the products? Now, it's a bit difficult to remember all of these, but we're going to refer back to the slide every time when you have a question. But let's continue. Here's another example. Same fictitious equation. A is reacting with B, and it produces C and D. If your delta H is negative, then we know that the forward reaction is exothermic and then the reverse reaction is endothermic. So indicate that in the beginning of your question if you know that delta H is negative. The second thing is, if you're going to increase the temperature, you know that an increase in temperature is not going to favor the forward reaction, but it's actually going to favor the reverse reaction. So do take note that the concentrations of C and D will decrease and the concentration of A and B will increase. So we're rather going to state that the concentration of A and B will increase because the reverse reaction is favored. And then we also need to take note that if we're going to decrease the temperature, the opposite is going to take place, and that the forward reaction, which is exothermic, is going to be influenced in a favorable way. And here we can see that the concentration of A and concentration of B will decrease, but the concentration of C and A will increase. Okay, so let's look at how the graph of an equilibrium reaction is influenced. Now, this is the reaction from the start, and here is the initial equilibrium being set up. Now, remember that a catalyst will influence a reaction by increasing the rate, and we have a rate versus time graph, so it will go directly up and then a straight line for the new equilibrium. If you see a sharp increase upwards and then you see a flat line again, then you know that the reason for that change is because of a catalyst. Okay, so remember that the catalyst has no effect on the equilibrium position. It's still the same equilibrium, it's just being reached a little bit faster. That is why the rate is higher compared to the previous rate. Okay, now if the reaction takes place faster, then obviously it means that the time for the reaction to reach equilibrium will now be shortened, or it will be less time. That's another thing that we need to know about the effect of a catalyst. And remember that here I have a solid line, and on top of the solid line, or slightly below the solid line, we have the reverse reaction. And the reverse reaction and the forward reaction, both of these reactions are being influenced equally by the catalyst. It's not just the one, it's both of them. So those are three important facts that we need to know about a catalyst and how it affects an equilibrium graph. Okay, now the next way or factor that can play a role that's actually going to influence the equilibrium graph is pressure. Now remember, you have to take note of the phases. In this case, I haven't indicated the phases, but let's assume that all the reactants and all the products are in the gaseous phase, and they will be influenced. So I'm going to add up the number of moles of my reactants, which is 4, the total number, and the total number of moles of my products will be 3. So on my reactant side is the greater number of moles, and on my product side is a lesser number of moles. Okay, if the pressure is increased, now I know that equilibrium will counter that increase, and it will the position of the equilibrium will shift in such a way to reduce the pressure. And in doing so, the side with the fewer molecules will be favored. And here you have to look at which side it is, and that will be C and D side. So there will be more C and D and less A and B molecules or concentration of that. So the forward reaction will be favored, and that can be captured. Increase in pressure, the forward reaction is favored, therefore the increase in the concentration of C and increase in the concentration of D. And that means the forward reaction, there we indicated, will be favored. It will be faster compared to the reverse reaction. Let's see what a decrease in pressure will cause. And here we can see that a decrease in pressure, the equilibrium position will shift in such a way to increase the pressure, which is the opposite. Now be careful when you use this statement. Don't say that equilibrium will shift to the left or to the right. You can say that the equilibrium position will shift. You can also mention that it will change, or you can say it will be altered in such a way to oppose the effect that the factor has on equilibrium. So anything like that, but do not refer to shift to the left or shift to the right. And then as a result of that shift, the side with the most molecules, gas molecules, will be favored. And that will be the reactant side. So in this case, you can also add by saying that the reaction, that is the reverse reaction, will be favored, or you can mention that there will be a higher concentration of the reactants and a lower concentration of the products. And we can summarize this. A decrease in pressure will favor the reverse reaction that will lead to an increase in the concentration of A and an increase in the concentration of B. So that just summarizes the effect of pressure on the equilibrium reaction. Okay. let's look at how temperature is going to influence my equation, and we're going to see what the effect is going to be. Now, before we start here, I've got A and B, C and D as products, same equation. If I look at the equation, I see delta H is less than 0. So that indicates to me that it's an exothermic reaction. And the value for delta H refers to the forward reaction. So the forward reaction is exothermic, and it means that the temperatures increase. Now, when we say temperatures increased here, it refers to the temperature of the container. Okay, so that means that this reaction is giving out energy. And the endothermic reaction will be favored if you decrease the temperature, and that means of the container, and it means that the products will absorb the energy or the heat, and then it will favor the reverse reaction. Okay, so once you add heat and you increase the temperature, the equilibrium will shift to reduce the temperature, and by doing that, it will favor the reverse reaction, or it will favor the endothermic reaction. In doing so, you will produce more A and B particles, or you will increase the concentration of A and B. At the same time, the concentration of C and D will be decreased. So here we can summarize it again. Increase in pressure, the reverse reaction is favored. Concentration of A and concentration of B are both increased. And that means that we will have the, okay, no, that will not be the forward reaction. That will be the reverse reaction that will be favored. Okay, so take note that this arrow is wrong. It should have been that one over there. Okay, let's move on to the next slide. Apologies for that arrow, that's in the wrong place. If I decrease the temperature by putting it in ice, what will happen? The equilibrium will shift once again. Take note that we always say, and we always try to answer them in the same way. In this case, we say again that the system will react in such a way that it will shift equilibrium by doing the opposite or opposing the factor that was introduced. And this means increasing the temperature. That means the exothermic reaction is favored, or according to our reaction, the forward reaction will be favored. And in doing so, there will be more C and D molecules, or the concentration of C and D will increase. At the same time, A and B will decrease in terms of molecules, or the concentration of A and B will decrease. Okay, so we can put that in a summary. A decrease in temperature, the forward reaction is favored, and the concentration of C and D is increased. Okay, now for this slide, don't forget that these two arrows must be opposite. Okay, this one must appear first when I talk about temperatures increase, and that arrow must appear once we talk about the decrease in temperature. Okay, how does concentration affect the equilibrium? And here we can see that if the reactant concentration is increased, then we increase the concentration of one of these reactants, and we can either say it's A. Whatever happens for A will be the same for B. The equilibrium position will shift, as we said before. The reaction that uses the reactant is favored. Okay, and A must then react with B so that we can convert it into C and D, the products, and in that way you get rid of the extra reactant that you added. So the forward reaction will be favored in this particular case. And here's a summary. Increase A or B, forward reaction is favored. The concentration of C and the concentration of D is increased. Now, if we're going to decrease the reactant, then the opposite is going to take place. The equilibrium is going to shift, and in doing so, it wants to increase the concentration, because we've originally decreased the reactant. The reaction that forms the the reaction that forms the reactant will be favored because initially we decrease the reactant. So the new equilibrium mixture that will be obtained will produce more of the reactants and it will produce less of the products. And in this case, the reverse reaction will be favored. Okay, and there we can see as indicated on the slide. In summary, we can say a decrease in the reactant A or B will favor the reverse reaction and therefore will cause a decrease in the product's concentration, or you could say it will cause an increase once again in the reactant concentration A or B. So it depends what you're going to write, and that is going to be correct dependent on what the question is asking you. Here we've mentioned both what's going to happen to the reactants and what's going to happen to the products. But we're going to see that later in the question. What you must also take note, here I've spoken about only the reactant, but the opposite will be true if we're going to use the same scenario, but in case of products. So if we're going to increase the product and we're going to decrease the product, the opposites will be true. Okay. Now, equilibrium constant is a mathematical way to express more or less where the equilibrium lies along a continuum. And the equilibrium constant will tell us if it lies more to the left or more on the reactant side. It means I have more reactants in my reaction container compared to products. If the equilibrium lies more to the product side, it means that I have more products and less reactants. Now remember, a chemical equilibrium never goes to the end of a chemical reaction. It kind of moves between the start of a chemical reaction and towards the end, but never reaching the end. Okay, so a couple of things that we need to know is the equilibrium constant. How do we write it? Do take note, it is square brackets, and then the exponents are the mole ratios in your equation. So for reactant A, which has a mole ratio of small a, that A is going to be my exponent in my equation. So remember, an equation must always contain the reactants and the products of the equation that you're dealing with. Don't say Kc equals concentration of the products divided by concentration of the reactants. Use the actual products and the actual reactants when you write the Kc expression for a reaction. And here are some factors that you need to know, of facts. So remember, only gases and liquids appear in Kc expression. The equilibrium constant does not have a unit, and large Kc values reaction in which concentration of products will be high compared to the reactants, and small Kc values indicate the opposite. Remember that there's only one factor that influences Kc, and that is temperature, and the Kc expression here is mentioned again. Do not write products divided by reactants. Okay. Now, that is what we've done for part 1. You need to go through it again, and please go to part 2 so that you can continue learning a little bit more about Kc and how we calculate it in our calculations and in questions. Thank you for now, and we'll continue with the second part after this.